So in the famous words of the Monty Python TV show, now for something almost completely different. What we're going to do now is we're going to take a look at a case study called the ImageStreamGang case study. And we're first going to explore how to solve this with parallel streams. And then we're going to come back around and re-explore how to solve it with completable futures. And there's a reason I'm doing this, because I want to have you really be able to do an apples to apples comparison between a parallel stream solution to a set of requirements and the completable futures version, and then we'll compare and contrast them across several different criteria. So we'll start out in this part of the lesson by talking about what the ImageStreamGang's structure and functionality is, and you can get this case study in my GitHub repository in the ImageStreamGang folder, and there's a couple different variants. One of the variants is based on Android. It's a really cool Android implementation, not unlike your web crawler example, although it's doing something different. And then there's also a console version as well. This particular ImageStreamGang case study applies several Java parallelism frameworks. It applies parallel streams and also sequential streams, because those are a no-brainer to do. And it also applies completable futures, and it also applies Java reactive streams. So it's kind of a Rosetta Stone of coolness to compare and contrast these different alternatives. So as you all know, the parallel streams framework uses the common fork join pool, and the completable futures framework may use the fork join pool framework. It doesn't have to. In fact, we'll see we have implementations where it isn't used at all. In this particular discussion, which is going to focus largely on parallel streams, we're going to discuss also how this case study demonstrates the integration of object-oriented and functional programming. And as always, we're going to try to look at software patterns as a way to help emphasize the key roles and responsibilities in this case study app's design. So what does this app do? Well, I've mentioned this app before, but let's go ahead and talk about it more systematically now. This app is going to apply these different parallelism frameworks to download, transform, store, and display images. And under the hood, it uses the StreamGang framework. And the StreamGang framework is something we've seen before in the context of the search StreamGang case study. So we're reusing the same framework, but now we're going to apply it to image processing rather than looking for phrases in the complete works of William Shakespeare. So here's kind of how the program works. And again, there's an Android version, there's a console version. They both work pretty much the same. The user is prompted for a list of URLs to download. The user supplies the list of URLs to download. The images are then downloaded in a pool of threads if they're not already downloaded from previous runs of the program. Then a bunch of filters are applied to transform the downloaded images to do things like embossing or sharpening or red eye removal or whatever type of image processing you want to do with them. And then finally, after things have been downloaded and filtered, then the transformed images or the filtered images will be written out to persistent storage, basically to files on the local device. And this particular framework applies a whole gaggle of modern Java features. So we'll talk about sequential and parallel streams, focusing on parallel streams. That's what we're going to talk about now. And this is a snippet of what the code looks like for that example. And then later we'll come back and look at the completable futures implementation. And you can see that the parallel streams implementation is a bit more concise than the completable futures implementation, even though they're both using some variant of the streams framework. And there's also other good examples of other things we've talked about, like lambda expressions and method references. And these are things we've covered earlier, but you'll see them pop up all over the place in the solution. So rather than writing this kind of nasty, anonymous inter-class style object-oriented code that's a bit accidentally complex and guaranteed to give you carpal tunnel syndrome, we can use the more concise functional programming techniques. Now, another thing that's important to mention here, and I haven't really spent as much time on this topic as I probably should in this class, but there's only so many things we can cover in the amount of time we have together. There's a bunch of patterns from the Gang of Four book and the various pattern-oriented software architecture books, the POSA books, that we apply in order to enhance our framework-based architecture for this case study. And you can find lots more about these patterns at the links below. Some of the patterns that are applied here are very, very fundamental, very essential to the design of the program. So for example, the The Java Streams framework is essentially the pipes and filters pattern, which is a pattern that was documented in the POSA 1 book, and it also reappears in the POSA 4 book. And you can also read about it at this paper down below at the link at the bottom of the page. And basically, pipes and filters takes the application's tasks and divides them up into a bunch of little standalone elements that can be connected together by data buffers and to form a data processing pipeline. Well, gee, that sounds like a Java stream, and that's exactly what it is. Java streams are basically a realization of the pipes and filters pattern. Of course, there's also the future pattern, which is used to define a proxy to a client so that when a service is invoked by the client, you get back the future. The computation can run in the background asynchronously, and then when the client needs to get the result, then it can go and get it or wait until it's ready or poll until it's ready or do a timed wait until it's ready. Various ways to be able to redeem the results of the asynchronous computation. Yet another pattern, and future appears in the POSA 4 book and the POSA 1 book. The resource pool, the POSA 2 book and the POSA 4 book. There's also a pattern called resource pool, which appears in the POSA 3 book, and this is used to prevent expensive reacquisition and re-release of resources by recycling the resources when they're no longer needed. So rather than creating something every time it's needed and then destroying it when you're done, you get it out of a pool, and when you're done, you put it back into the pool. So it can be recycled and reused by some other part of the code. So that's obviously the pattern that underlies the various thread pools we've talked about. Those are all POSA patterns. Then there's also some other very essential patterns that are from the Gang of 4 book. So template method pattern, hopefully you're very familiar with the template method pattern from earlier courses where you define the overall structure of a method and allow subclasses to refine or redefine some of the steps in that method. There's the factory method pattern, gets used all over the place, which encapsulates the concrete details of object creation inside of a factory method rather than having the clients create the objects themselves. And obviously there's many examples of that all over the place. We've mentioned factory method over and over again when we create things like collectors and streams and iterators and so on. Some other pattern that's used here, which I won't talk about as much as I probably should, but it's pretty cool. It's the decorator pattern. And you can use this pattern to dynamically add behaviors to objects without affecting the behavior of other objects from the same class. And we use this particular pattern to decorate the output objects in order to apply various image transforms or filters to them before they're written to disk. There's also the singleton pattern, which is not as essential as some of the other ones. That's just used to make sure you have one instance of a class and have a global point of access to it. Probably a good idea not to get carried away with singleton, but it does come in handy from time to time. Yet another pattern that's used under the hood by parts of Android as well as parts of Java's concurrency frameworks like the executor framework is the command processor pattern, which basically packages up application functionality into an object and then allows that object to be applied in different contexts, such as later point of time and a different thread and so on. And this is used by some of the concurrency frameworks you get with the object-oriented parts of Android and Java. So we're going to walk through the code. Be aware that there's actually a lot of code. We're not going to walk through all of it, but as always, there's lots of code, lots of classes, and if you're not careful, you can drown in a sea of complexity. And obviously, we want to avoid that. So it's important to be able to look at the software design from different points of view in order to be able to see how the pieces fit together more effectively. So here's kind of a snippet of the key classes in the program. And we're going to look at this from a couple of different perspectives, including its pattern-oriented design, the data flows, and then, of course, we'll also do detailed code walkthroughs because that's where the real ground truth arises, the actual code. So you may want to go back and rewatch this stuff to see how it all works. We'll also visualize the data flow, which is my favorite way of trying to give you a right brain perspective on what can otherwise be a pretty left brain linear way of looking at source code. Okay, so you can get the source code here. We'll look through the key parts there as well. So that's the end of the overview of the case study, and that went on a bit long, but it's important to see the big picture before we start diving into the different details we're about to cover.